Hello guys, so welcome back to my YouTube channel. I know it's been a while since I made a video. I apologize. I've just been really busy with my online class. I'm taking data structures and algorithms this month, so it's been pretty intense. Let me just say that. So basically for this video, this is going to be one of the lab videos. So I'm just going to talk about the recent lab that I did, because I think it's like really useful and very like in depth about like data structures that are pretty useful in the real world, I guess. So I'm basically just gonna show you guys my code and like run it and show you guys what it does. So for this lab, it was basically like minimum priority queues that we were dealing with. So essentially, like a minimum priority queue is used to like schedule jobs, for example. And like how a queue works is it's basically like you can implement it several different ways. You can use a vector, you can use a linked list. So basically, like when you insert into a queue, you insert to the back, and then when you want to remove something from the queue, you remove from the front of the queue. Like just think like a queue of like a line of people. Like that's basically how it works, and that's how we had to code it. So I'm just gonna pull up my report so like I don't forget anything. Okay, so basically what I'm gonna do is I'm gonna delete a bunch of stuff here, so then I can show you guys like what it does. You guys can see it running. I think that should be fine. So let's start with the implementation of a linked list. So you know, like a linked list is a bunch of nodes connected by pointers and stuff like that. I'm not really going to get into that right now. That could be for like another video. But so I have like the struct, the item, the node. I labeled it item. This is an implementation of a doubly linked list. So here's the linked list class. You have a header and then you have the tail, which indicates the beginning and the end of the list. And that's going to be useful for like the insert and like the remove functions and the empty function. So this is my constructor. These are just all the other functions that I thought were necessary to like implement this code, and then I have like an exception here. So for the insert, let's start here. So for my insert function, you can see like on the nodes I have to basically like say the runtime and stuff like that. So first it checks like if the linked list is empty, and like how I defined an empty linked list is like if the header node, if the head's next points to the tail, then basically like it's empty, there's nothing there. So you just add it, you just insert a new node. And then the next like else if is if the value at the last node is less than the value of the one you want to insert. So you just insert it like right to the back. So like you do all the pointers and like you do the pointer logic and stuff like that. And then you add it like to the back. So basically right before the tail. And then this one is if like the value that you're trying to insert is in the middle somewhere in the list. So basically like you have to have like pointers for like the node that's changing and then the node like right before it. So then if you find it, then you gotta insert before, and then you go to this function, and then there's like a condition here. So like if it's actually the first node, then you go to insert first. So it's just like a little bit like more concise, I guess, like so you can actually see what's happening, like the movement from function to function. I thought it was easier anyways. And this is because I do this like this because I want to have it sorted upon insertion. So that's why we have to do all this. If I was just like entering in random values, like I would just insert it to the back basically. And then, so that's why my remove min function is just O of n. It's constant because it's already in order. So you just have to remove the minimum, which is at the first index of the list. So yeah, that's basically like what I had to do. And then for my vector implementation, it's pretty similar. Has a little bit less of functions because it's a little bit simpler to implement a minimum priority queue using a vector. And this is like a code that I tried to make it sort the vector first, but it was just not, I don't know why it wasn't really working. So basically what I do is I insert the item into the back of the vector. And then when you want to remove it, then you have to search the entire vector for the minimum and then you just return it. It's like the opposite of the linked list implementation. And then for my binary heap implementation, this is where I had to create like a binary heap using a binary object. So my binary object was implemented based on a vector. And these are all the functions that I used, plus the exception in case like you wanted to access or you wanted to remove something from the vector and it was already empty. And then this is like the struct that we were given for my assignment. And I just added these overloading operators because that'll help you a lot when you're doing these comparisons here. So once you overload them, you can basically like compare them like as if they were ints or something like that. So a binary heap is basically like you can think of it like kind of like a tree, and then it's like in order. If you want a maximum binary heap or a minimum binary heap, you have to like change the implementation to fit everything like that. So for my remove min, I think from my implementation, yeah, so basically like when you're inserting something into your binary heap, you insert it into the back or like the end of the heap at the bottom. And then to get it in order, you have to perform walkups. And that's basically like the worst case of that is the height of the whole tree, which is O log n. So you perform walkups, and then when you find the correct position, you stay there. And then based on my implementation, since it's a minimum priority queue, the root node of the whole tree should be the minimum. So in the remove min, all you have to do is like take out the minimum. Well, first you swap it with the bottom one, with the last one, and then you remove it. And then you have to perform walk downs with that one that you just switched, so you can replace everything back in order. And that's basically all the logic I have here. You can see like my vector of class, let's say CPU jobs, of struct CPU jobs. You have to compare them using this operator. So they're not int, so usually you would get an error. But since I overloaded them, where is the overloading? Here, based on like the categories or like the specifications for my assignment, then you can compare them and then it does the job for you. And then I have a output operator, so like when you do you want to print them, you can just use this and then it will go here and then print it nicely however you want it. So yes, I'm going to run this and I'm going to show you guys like how it works and what it does. So right now you can see that these three files are empty. So in my main, this is just like a couple phases. In my main, you can see that I have to write into like a new file, and like I print out all the priorities based on like the classifications that I needed to do. And then these are just like run times that I have to do, these timings of each different implementation of the binary heap, the linked list, and the vector implementations of linked lists. That's all that I had to do. So yeah, I'm just gonna run this for you guys. Please ignore this. I don't know why it's like that. So negative O, what is it? Okay, so this is just code to test my priority queues. So look here, we're inserting into the heap. They're all out of order. But then like when you remove them all in order based on like the implementation. And then this is just like, oops, this one here is for the linked list. They're all not in order. And then when you remove them, everything should be removed in order based on like from minimum to maximum, because it's a minimum priority queue. And then this is just a little sample of my CPU job implementation, or my CPU job binary heap. So what I had to do is like the priority was the main thing. So the less the priority, the smaller the priority, the higher the, well, yeah. Okay. So basically it's the smaller the priority, like the higher it is on like you have to do it. So you put it at the top. So as you go down, these are like the ones with less priority. And then like if they have the same priority, you check the job ID. So if the job ID is less than the one you're comparing it with, it goes first. And right now it's basically like stalling or just inserting a bunch of things into the binary heaps or whatever, because these are literally like 10,000, 1,000, so they take like a decent amount of time, but like they're still fast enough that like they were decent. And then like if we check the files, you can see that the correct output got printed into each file. So everything now is in order based on the priority that we've set. And yeah, these are the ones that we deleted. So now they're all in order. Let's see if it's running. It'll probably take a little bit less time because I'm also running this recording software, so that'll also affect it. Oh, sorry. Okay, yeah, so that's gonna be the extent of this video. If you guys want me to go more in depth on linked lists and minimum priority queues, I would gladly do that. This was just supposed to be like an overview of the labs that I've been doing, because I think they're actually really useful and really interesting. So yeah, and I'm gonna try to make more videos, but with my class it's pretty intense, so like I don't really get as much time as I would want to. But thank you guys for watching, and I'll see you in the next one.